Hello, this is me Susan Frista and welcome to my channel. Today I'm going to discuss or talk about logarithms and internal computation of logarithms, how computer implement this logarithm function to calculate the value of it. Okay, let's start on the discussion on the topic. So what actually is a logarithm? We go a brief introduction on it. Basically, you can say that to what power raised to what power. So this is the equation of a logarithm. So I have written a simple logarithm equation to illustrate about what the logarithm is. So we can see here the value of c, which is the power here. A log of base a of value b is equals to c. So what we correspondingly say that to what value of c we can raise the a. We can raise the a to what value of c, so we can get value b. Let's see a log of log 10 base of 10, okay, of 100. So to what power of 10? To what power of 10? So what is the power of c? 10. We can get 100. So we can do that, right? So 110 into 10 are equals to 10 to the power of 2. So the value of c is 2, right? So we're gonna get the log base of 10 to the 100 equals to 2. What if I add the value 0 here? So we have to multiply again by 10, okay, giving to it to the 3, right? So we're gonna get here 3. So this is the basic of logarithm. Okay, so my question or the objective of this video was how this function is implemented in computer. There are basically three types of implementation. One is the Taylor expansion, second is the rational implementation, third is the tabular implementation. We're basically going to talk about the first one, the Taylor expansion. Okay, how the Taylor expansion is used to calculate the value of logarithm. Before discussing about the Taylor expansion, how do we calculate the Taylor log function by the Taylor expansion, we need to know the derivative of log. There are various ways to get the derivative of log. One of them is using the first principle of derivative. So here it is. So this is the formula of the derivative, first principle. Okay, it is the raise divide by run, and run x1, sorry, here we have done what we have done is x2 minus x1 equals to adds, and this adds tends to 0. That means it's going to be very small to get a continuous function. Okay, and what about the here we got the f x2 and minus f x1, right? This is the first principle of derivative. So if it is the adds, what's this? x1 minus x1 plus adds. Now after simplifying using the log rule, log x plus s minus adds, this we're gonna get the quotient of log rule, we got this. Okay, and after this simplifying we're gonna get this. Now we have a small tweak here. We're gonna assume this adds by x, adds by x is t, right? We're gonna assume x by x equals to t such that x equals to xt. Also, when x tends to 0, when x tends to 0, this tends to 0, 0 at t tends to 0, right? Because this all gonna be 0. Okay, so that's why we're gonna go the corresponding t when we substitute adds by x equals to t. Okay, so when we substitute this t and x equals to xt, right here, and t gonna be tends to 0, right? We simplify now. We simplify this 1 by x comes here, 1 by x comes here, remaining the 1 by t log t, and this 1 by x is a constant because we are dealing with t variable right now, so we only consider, or we are only interested on t. So now this expression, what is this expression? This expression is the expression of an exponent. You can do some research on that, why it is. I'm not gonna go because it's another topic for the discussion. So what we get is, this is the value of e, right? Now for the base exponent, we are dealing on the log. We have no any specific base of log. So now when we specify the base of log is exponent or natural log, we're gonna get this log e gonna be 1. Ln, this log base e is ln. Okay, so this is gonna be a 1. So what we get here equals to, we get the derivative of natural log is 1 by x. Now why we gonna use this log? It's because we're gonna need this derivative in the Taylor expansion. Okay, so what is the value? What is the Taylor expansion? So this is the Taylor expansion, right? This is the Taylor expansion. So how did we get the Taylor expansion? So there is we derived this Taylor expansion by the power rule. This is the power rule, and we're gonna take a derivative of it, derivative of this, and here it is the center at C. You can see it is centered at C. What if it can C is equals to 0? If C is equals to 0, it is centered at origin, right? Origin. So when x equals to 0 and c equals to 0, we're gonna take we're gonna get the value here of first derivative and second derivative. After generalizing the value here, and substituting the value of derivative, a value of coefficient a1, a2, a3, we're gonna get this. Okay, this a0 equal is this, right? And this a1 equals to this, and this a2 equals to this. Okay, so this is how we get the Taylor expansion. We now know how Taylor expansion is derived from the power rule. Now after that, we expand the logarithm function using Taylor expansion. Okay, first we have to take the derivative of some level to know the pattern. Okay, first we take the first derivative, second, third, fourth, and fifth. We can take all the way to we need the precision or accuracy. The more we take the extent of this expansion series, the more accurate and the more precision of the value of log we get. Okay, so for the sake of simplicity, we're only gonna take the fifth derivative. After we take the derivative of them, so I don't need to explain them. Okay, now further, the centered c equals to 1, notice this c equals to 1. Okay, I put the c equals to 1 because I need to get the value of log. I need to get the rid of log 1. Okay, because here is the fc. We need to put the value of log here. Okay, I need to get rid of this because I need to center it 1, and because of centering c equals to 1, there are some limitations of this expansion that I'm gonna talk at the end of the video. So we substitute the value here. Okay, this is how is the log expansions, and this is gonna be 0, and we get the final series of log. Okay, this is the final series of log, Taylor series of log. Now we need to implement this series in algorithm or in a code. So I have already done this in the Python. Let's see here. I'm not gonna explain each and every bits of this code, but I'm gonna put this in the GitHub. Okay, and you're gonna find this logic of the code by yourself. If there are any questions or you really didn't understand the code or implementation of this series, please feel free to ask me in the comment. So look, this is the value. Okay, when I put this, it's gonna build natural log of 1 equals to 0, right? So we're gonna get a value. Look, this is fast. Okay, so I told about a c equals to 1, right? We assume that c is equals to 1. Okay, by assuming c is equals to 1, first we get the rid of this first element. Okay, and there is a incapability of this expansion of this method. It is incapable of expanding or giving a value greater than or equals to 2. Okay, 0 and 2. Sorry. So this is only valid to this constraint. Okay, out of this range, our series x and ln x will not converge. Okay, will not converge. The series only converges for this condition. Okay, so let's see how it diverges. And we can see here when x reaches the value 2, after that we can see then a divergence behavior of the series. Okay, look how drastically or how roughly or how extravagantly they diverges. And this pink is the exact value. This is on the range, right? This is the track. So it was the limitation of Taylor expansion. As this is a Taylor expansion, there are other rational ways. One of them is by Mayer Goldberg. He published this paper, Computing Logarithm by Digit, where he proposed this expression where d is the base and m is the iterative element. Okay, so if you are interested to learn more about this, you're gonna Google it, and it's a paper you can read and understand how it works. Now I have implemented this to show the short demonstration of it. Here it is. This is the code, and I have also included this code in the GitHub. I put the link in the description. So I have set this base at 10. So this is the 10, okay. For the 100 it's gonna be 2, and for the 10,000 it's gonna be 4, and that's 25, it's gonna be this. So it's actually good algorithm. I think it's much better than Taylor expansion. This much for today video. I hope you liked it. This was my first video, and in the coming days I will try to make it much better and much clear and comprehensive. And for now, take care, goodbye, have a good day.